Right, hello again. In this video, we're going to be starting on now with the main core material of National 5 Physics. So previously we looked at just some of the core skills you need for physics. Now we're looking at the actual core content. Before we do that, we'll just have a quick look at an overview of Nat 5 Physics, give you a wee idea of what's actually involved. So at Nat 5, physics is split up into three main topics, which you can see here. We've got waves and radiation, electricity and energy, and dynamics and space. Now there's a wee bit there about what's in each of those topics, and you can probably guess yourselves. What we're going to be starting with is the waves topic. Now, waves is something you have seen a lot of before, especially in S3. But with this being Nat 5 now, we are of course going to be going into a lot more detail into this. Before we start, really powering through into that detail though, something I just want to make sure you're all comfortable with is the idea of speed, distance and time. The reason we want to hammer this concept home is that this is a fundamental formula. What that means is it comes up in so many of the different topics, not just in waves. So it's one of the formulas you really need to be very comfortable using. Okay, you will be given the formula, but you really need to be very, very familiar and happy to use it in all the different situations we see it in. Now, as you know, the formula is distance equals speed times time. And if you know two of those, you could rearrange your formula to work out the other one. Instead of writing it all out, we can just do d equals vt, where d is your distance measured in meters. V is measured in meters per second because it's a speed, and T is measured in seconds. Now, you are not told the units. You need to remember those because remember in physics, the unit is just as important as the actual value you've got at the end, and you're going to be throwing away that last mark if you don't include your units. Now, we'll look at a wee worked example of this, but first, let's just remind ourselves how we rearrange that formula. And we do it the same way we rearrange lots of formulas in physics, and that's by using one of those really handy triangles. So if we draw ourselves a triangle and put the variables in, we've got d for distance on the top, then we've got v here for our speed and t for our time. And what this does is it tells us that if we want to work out the distance, we cover that up, and that tells us we've got speed times time. Then if we want to work out the speed, we cover that up. It tells us we've got distance divided by time, and same for working out the time. Now, this is something you should be very familiar with. So we'll very quickly look at a worked example of it. So Dave is traveling back from work on his magic carpet. Look at him there, so happy to be going home. It takes him 45 minutes. He lives 40 kilometers away from his work. How fast was Dave traveling? Very first thing, like always, pop down what we know and what we're trying to find out. But there's a few little tricky bits here. Okay, the distance was 40 kilometers. We need to remember that kilometers, that means times 10 to the power of 3. We don't know the speed, which we're trying to work out. And then the time was given to us in minutes. So we need to remember that the standard units for time is seconds. So we have to times our minutes by 60 to get the time in seconds. Okay, then I've skipped straight to the rearranged version of the formula here because it's one you should be familiar with. If we've used our triangle, we get that speed is distance on the top and then divided by time on the bottom, and we just substitute in our values, and that's going to give us at the end that our speed is 14.8 meters per second. Remember, units. Also, when you're doing things like this at home or in class, or especially in the exam, make sure you're not putting too many numbers here. Remember what I said in the last video? You want to be using 3 significant figures in your answer unless the question says otherwise. So we don't want a whole long train of decimal points here after the number, because that's just in the way. We don't need that. So that should have been very familiar to you. Before we start looking at waves in a bit more detail, just want to make it really clear how we solve problems using a formula, because if you stick to this method, it's going to maximize the marks you get. and it's going to reduce the chance of you throwing away any little silly marks. So step 1 is always fully read and understand the question. It's incredible how often someone doesn't read the question properly and they've got the wrong end of a stick and they start to work out a completely wrong thing. Second, write down the information that is given to you. So that's what we do at the start of every question. We write down what we have and what we're trying to figure out. Using that, we choose the correct formula. So look at what you've got and what you're trying to get, and look through your data sheet to see which formula has those things in it. Once you've chosen your formula, write it out. You get a mark just for writing down the correct formula, so never forget to do it. Then complete the substitution of all your known values, remembering to convert them if you need to, and then pop it in your calculator. And when you write your final answer down with its units, this bit here is important. It says underline, doesn't necessarily have to be underlined, but just make it really clear what your final answer is. Okay, pretend the person looking at it is stupid and they can't follow it. Really point it out and make it clear to them what your final answer to the question is. Right, with that out of the way, let's start talking about waves. Let's have a wee think about what waves actually are. So, waves. Light and sound are forms of waves, but the key property that we have to remember when we're thinking of waves is that waves transfer energy. So, waves can be described as a disturbance or something that is travelling through a medium. It could be travelling through the air, it can be travelling through water, through glass, through the earth. But the key thing is that they are transferring energy. Waves can transfer different types of energy, and the ones we're going to be more focused on are ones that transfer light energy or sound energy. And this here is your typical drawing of what a wave looks like. And if you think of when we've done the electromagnetic spectrum before, you'll have seen something like this. And at one end, the wave bits here are all spread out, and then as you get to the other end, they'd get closer and closer and closer together. Okay, that's your typical drawing of what a wave looks like. And there are some key points on the wave that we need to be able to define and recognize. So, at the top of the wave here, we've got the crest, sometimes called the peak. At the bottom, here we've got the trough, that's the lowest point on the wave. Then this distance here, so if we say the wave started here and it went up, down and back up before it got to sort of the same position it started in, that distance there is called the wavelength. Okay, so that's the distance it took to do one complete wave. And can you see that that distance there, the wavelength, I'll just get the pen tool out, that distance there is the same as this distance here between those two peaks. That's the same as that, and it's also the same as this distance here between those two troughs. So wavelength is basically the distance between two of the same bits on a wave. Okay. And then the final bit we want to look at is this here, and it's this. We call that the amplitude, and that's how high the wave is above this middle line, the rest position. So we want to write down an actual proper definition for these parts of the wave, and that is as such. So crest, the highest point of a wave. Trough, the lowest point of a wave. Nice and easy to remember so far. The amplitude is the height from the rest position. So the rest position is that middle line. So the amplitude goes from the middle to the top, or from the middle to the bottom, but it does not go all the way from the top to the bottom. And then finally the wavelength. Now we've popped in a little symbol here. That's going to come up later in the waves topic. You might have seen it before. This symbol here is lambda, and that's the symbol we use for wavelength. So wavelength is the distance until a wave repeats itself. So it's this distance between 2 points that are basically the same on a wave before a pattern starts again. At this point, there are 4 key terms we're interested in to describe a wave. If we can talk about those 4 parts of a wave, that's going to tell us a lot about it. Okay, it's going to tell us a lot about its shape and its properties. At Nat 5, we want to be thinking about waves in a little bit more detail than just the idea of waves we've encountered in S3. So we want to think of what different types of waves we have. And I don't mean here light waves or sound waves, I mean more about the actual shape of the waves. And this brings us to something called longitudinal or transverse waves. So waves can be split up into 2 types, longitudinal or transverse. Now, longitudinal waves, they vibrate, they move in the same direction that the energy is going in. Okay, so an example of a longitudinal wave is sound, right? This will become a little bit clearer in a second what I mean by this. Transverse waves, they vibrate at right angles to the direction of the energy. So if the energy is moving one way, the wave is actually vibrating or moving at right angles to that. So radio, television, water waves, all light, they are all transverse waves. They're the type of waves you use most often, okay? We encounter more frequently. And they're the ones that match your standard idea of a wave looking like this. Very, very bad drawing. That's a transverse wave. So we could use a slinky to demonstrate the difference between them, which is a really fun experiment we do in class. Okay, I'm going to put a link to a video that's going to help this, but if you imagine there's 2 of you stood in front of a class with a slinky and you're holding it, then if you're just pushing the slinky back and forth between you, that's transverse, okay? There's no actual up and down movement. The only movement in the slinky is back and forth between you. Okay, then if you were to start wiggling it up and down, trying to make this sort of wave pattern you see here, that would be a transverse wave because all the energy would be starting here and going this way, but the wave is actually moving up and down like this. Now, this diagram here shows this a wee bit better. So at the top here, wave A, this is a transverse wave. So the direction of a wave is going along here, starting at the left and moving to the right. But the particles are actually just moving up and down. Because they're moving up and down, at the same time it's moving that way, we get this pattern. It's moving up and down, up and down, up and down. At the same time it moves this way. So that's a transverse wave. Longitudinal wave, like sound, is wave B here. So it's going in the same direction as the one above, starting at the left, travelling over to the right, but there's no up or down movement. The particles are going backwards and forwards like this. And what that means is, as they're moving backwards and forwards like this, as they go that way, sometimes they all bunch up like this, and then sometimes they stretch out wide like that, and then they bunch up again, and they stretch out, and they bunch up again. Right. And so that's how sound behaves. That's a longitudinal wave. Okay. Now we've covered the key differences between transverse and longitudinal, and remember to watch the other video which will make it a little bit clearer with some animations, and we've talked about the key properties of waves. Let's go back now to thinking about the idea of speed, distance and time. I said that was a fundamental equation and you could use it in lots of places. First place we're going to use it is with this, is with the idea of waves, because waves follow that formula. Waves are something that is travelling throughout the world, so they've got a speed as they travel, they're travelling a distance, it's going to take them a certain amount of time to travel that distance, so we can use our speed, distance, time formula to work out stuff about a wave. So let's have a look at that then. Let's do a worked example. So our first example, Jamie screams as loud as he can. His friend Sophie hears it 4.5 seconds later. How far away from each other are they? Now, as always, we're going to start with writing down what we have and what we're trying to find out. So you'll notice something immediately here. I've written down that we have the speed 340 meters per second. This was not in the question. This is something we need to know. Okay? It's saying here that Jamie screamed as loud as he can. So what type of wave are we interested in? It's a sound wave, because someone's hearing the sounds he has made. Now, one fact that we need to know is that sound has a speed. Its speed can change depending on what it's in. So the speed of sound in air is different to the speed of sound in water or through the earth. And you are given those different speeds. But you need to know that the speed of sound in air is 340 meters per second. So if Jamie and Sophie were stood 340 meters away from each other and Jamie screamed, Sophie would hear it 1 second later. She didn't hear it 1 second later though. The time was 4.5 seconds. The distance is what we're trying to figure out. So let's write down our equation. D equals Vt. And then we'll substitute in our numbers. V is 340, T is 4.5. Pop it in your calculator, and that gives you that your distance is 1,530 meters. So that's how far away they are from each other. Okay? Simple speed, distance, time equation, but now we're using it for waves. Let's look at a slightly trickier worked example then to finish off. In our second worked example, a boy is standing in front of a wall. He shouts and he hears the echo 0.17 seconds later. How far away is the wall? So he's hearing the echo. When he's hearing the echo, that's the sound coming back at him as bounced off the wall. Okay, so again, let's pop down everything we know. He shouted. It's still sound, so the speed is still 340 meters per second. He heard the echo 0.17 seconds later. Then we're trying to work out the distance. So again, pop down the equation and then substitute in. So we've put in 340 for the speed and 0.17 for the time. And we work that out and we get that the distance is 57.8 meters. Now you'll see here I've divided it by 2. Can anyone think why I've divided it by 2? So I'll just give you a few seconds before I actually go and say why. But there is a reason. Okay, so I'm going to do a little sketch on the side here. As I do that, see if that helps you think why it's divided it by 2. Anyone got any ideas after watching that? So, what's happened is, this is our boy here, our very, very well drawn boy, and this is the wall, and he's having a wee shout. So as he shouts, the sound leaves him, it goes along, and it hits the wall. Then, after it's hit the wall, it bounces back to him so he can hear the echo. And so that whole journey has taken 0.17 seconds. But that was the time for it to get to the wall and come back. So what we need to do then is divide it by 2, because we don't care how far away it is to the wall and back. We only care about how far away is the wall. So it's just the distance one way we want. So we divide it by 2. Then our distance is going to be 28.9 meters. Again, make sure you underline that or make it clear in some way. Right, that's where we're going to finish today with waves. We'll continue with this and introduce some new equations next time. But for the time being, the key bits to remember are your definitions of the 4 different points of a wave. It's 4 different properties, the difference between transverse and longitudinal, and then how you can use your standard distance, speed, time formula in conjunction with waves. Okay, so again, thank you for listening.